Alright, section 1.6. In case you're absent or need to go back and review, maybe the test is coming up or something, I don't know, but here we go. The product and quotient of powers. Okay? The product and quotient of powers. It's tough to, like, especially if you've never learned this before, it's tough to know what that title means, but I promise you it'll be much clearer, if not crystal clear. Few Good Men reference. Crystal clear. Well, crystal is what the line was. Sorry. But it'll be crystal clear, what the title sort of means. And we just do the examples and stuff, okay? Because it's really all about the examples. How to simplify a power with multiplication and division. Okay, so here's what we're getting at, really. So, already going to see. If you are doing 10 to the 5th times 10 to the 2nd power, okay, what does that actually mean that you do? Okay, so again, we are multiplying, because that's what the word product means, just saying. We're multiplying something together where powers are involved, or exponents are involved. So let's see what happens with all this. So what is 10, let me ask you something. 10 to the 5th power, what does that mean? How do you kind of describe what 10 to the 5th power means? Well, doesn't it mean 10 times 10 times 10 times 10 times 10? And then we're multiplying to these 10s 10 to the 2nd. What does 10 to the 2nd even mean? What does it mean to raise 10 to the 2nd power? Well, it means that. Another 10 times 10. Well, guess what? If you put these all together and made them all the same color, if that's what helps, what do you got? 10 times 10 times 10 times 10 times 10 times 10 times 10. Isn't that 10 to the 7th? Yeah. And just another example, wouldn't that be 10 times 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 10? And when you put them all together, wouldn't that just be 10 to the, what, 9th? And then 10 to the 1st times 10 to the 5th, wouldn't that just be this 10 times these 5 10s to end up with 10 to the 6th? Yeah. So, do you see a pattern? Because there's no way I'm writing out 50 10s and then another 4 10s. So, what do you think the final answer would be for 10 to the 50th times 10 to the 4th? Just imagine having like 50 10s, all multiplied together times another 4 10s. Wouldn't that be 10 to the 54th? That's what it would be. And what did I do as a shortcut, basically? Didn't I just add the 50, the power of 50, and the power of 4? Yeah, basically. So that's going to be a really, really useful shortcut. When the base is the same, like these are all 7s, and all these are more 7s, and you're doing these 3 7s, and then another 10 7s, all next to each other. And when that's the case, in other words, when the base is the same, and we're multiplying bases together with exponents, all you got to do is add the powers and get eventually 7 to the 13th power. Okay, and that is actually a number. It's probably a big number. So for right now, we'll just leave it as 7 to the 13th power. Number 2, same idea. It's the bases match. It's these 5s times these 5s. So all you have to do is add the powers and get 5 to the what? What's 8 plus 11? 19, So in order to, again, we're multiplying, but in order to do this multiplying, you're going to add the powers of the same bases. So over here, wow, that's a huge number. So 3 to that power times 3 to that power. You add the powers and get that as a final answer. I'm definitely going to leave that as that because that's a huge number. that I bet the calculators won't even be able to handle. Ooh, now we're getting interesting. Okay, so we have x times x to the 13th power. Think about it, people. If you were to write this out and expand it, there'd be this x here, and then another 13 factors of x. How many factors of x total would that be? Right? Now, let's talk about it in terms of the shortcut. And by the shortcut, I mean adding the powers. What's the power here? That's a key thing to understand going forward, okay? What is the power? It's invisible, but it's here. What's that power? It's a 1. So, if you're just doing that shortcut game, you would add the powers to get 14, okay? Which is what you should get if you expand it all out. This x and then another 13 x's, 14 x's total. But again, when you consider what the powers are, all you have to do is add the powers. Okay, here, number 5, we're getting a little bit crazier, but we're multiplying all this together, and we want to kind of, I guess the word would be simplify it, So we want to multiply together whatever we can multiply together and get a simpler answer. So look, I pretty much can't do x to the 3rd times y to the 8th. These bases don't match, so you can't simplify them together, and have a final exponent. But you can do x to the 3rd times this x to the 2nd, and when you add those powers, you're going to get x to the 5th. And you can do this y to the 8th times y to the 10th, and simplify those y's together, multiply those y's together by, again, adding those exponents, and this would be as final of an answer as we can do. X to the 5th, y to the 18th. Same thing over here, right? Hey, it's the same base. I know it's looking weird, but the base, even though it's a fraction, is still the same base. So when we add those powers and get 3/5 to the 44th power, and again, these parentheses are vital to include, because if there was no parentheses here, how would you know if this power only applies to the 3 or the entire fraction? See, obviously the powers apply to the entire fraction, not just the numerator, and so you need those parentheses, people. All right, changing gears, I guess, at least a little bit, to dividing. All right, so let's kind of really look into this in depth and look at what's going on behind the scenes when you take 10 to the 8th and you write it all out, and you take 10 to the 6th, which is now you're dividing it, and write it all the way out. Okay? Do you know what happens from here, or what you could kind of do from here and approach it in a way? You could do, 10 divided by 10 is really what? You could do this 10 divided by that 10 and get really 1. 10 divided by 10 is 1. And then you could do that 10 divided by that 10 to make really 1. And then that 10 divided by that 10. And that 10 divided by that 10. And those would divide out to equal 1. And those would divide out to equal 1. And that's all the dividing or canceling you can do. And so what you're left with after all the canceling is 10 times 10 in the numerator. And so what's 10 times 10? 10 to the 2nd. At least as far as exponential notation goes. And it's something very similar is going to happen here. If you write it all out, you're going to have 10 times 10 times 4 factors of 10 up here, and down here only 1 factor of 10. So there's only going to be one little instance of canceling, to be left with just technically 1. And so what's left over after all the dividing or canceling is 10 to the third. So I know we only did 2 examples, but do you see a pattern? Like, do you see a potential shortcut? What do you think? Do you see a potential shortcut going from 10 to the 8th over 10 to the 6th to just jumping to a final answer of 10 to the 2nd, and then 10 to the 4th over 10 to the 1st, and just kind of realizing how we just get to a final answer, skipping all this part? Do you see a shortcut? Well, there is. And if you simply have a common base with a power over the same base to another power, you can just subtract the powers, So, in other words, to divide common bases with powers, you subtract the powers. And so this is going to end up being, let's see, 17 minus 2, 15. Final answer, which is, again, that's going to be what, a 1 followed by 15 zeros? Big number. So some quick examples, people. Common base, 5 to some power over 5 to another power. We can subtract the powers as a shortcut and end up with 5 to the 4th power. And let's just leave it like that. Let's just leave it in exponential notation. Even though that's what? 506, maybe. I don't want to be wrong. I think it's 625, but whatever. Let's just leave it as 5 to the 4th power. Again, same base, so you can subtract the powers and just get 6 to the 2nd power, which is 36. Number 3, again, same base divided by the same base, so we can subtract the powers and get 17 to the 54th power, I do believe. Huge number, but let's just leave it as that. All right, let's make sure we do examples like this. So again, what power is right here? Because it's x's over x's, common base. I'm going to do 13 minus what? What power is here? 1. So 13 minus 1, final answer would be x to the 12th power. And you would definitely confirm that, and you would see that if you literally expanded this out and wrote 13 x's, and then this x would cancel with one of the 13, and you'd be left with 12 factors of x, and therefore x to the 12th power. Anyway, so we can divide this, and we can divide this, and at least get, I'm going to write below here. Now look, you would do the top exponent minus the bottom one. What's 3 minus 7? 3 minus 7 is actually negative 4. So we have x to the negative 4th power. That's right, the negative 4th power. And for the y's, we end up, when we subtract the powers, we get 5. Now, a little bit of foreshadowing. We're going to leave this as is for now, but guess what? At the end of the day, not this day, but at the end of the chapter, I guess, at the very latest, but sooner than that even, it's not going to be okay, USA, to leave your final answer with a negative power. So eventually, very soon actually, over the next few days, I'm going to show you how we deal with a negative exponent. But for right now, let's just leave it as is and move on. Hey, check this out. We are dividing. I know it's not written as a fraction, but remember, the fraction was dividing, so this is dividing also, just using a different notation, I guess, the actual symbol. And that still means we're going to take this common basis and realize that we can subtract the powers. So make sure you have parentheses. And when we subtract the powers, we get, I believe, 9, the 9th power. Ooh, And that would be it for the video, because after that we would do some notes at the board and stuff. Okay? That's it for section 1.6.